Hello. In this next set of videos, we're going to be looking at the topic of complex numbers. So we're going to investigate exactly what complex numbers are, try to give a bit of motivation for them, and ultimately look at some really interesting applications that you can use complex numbers for. So to start off, a little bit of motivation. Once upon a time, x plus 1 equals 0 had no solution. Now, you might not believe that, but that was indeed a thing. People didn't believe that an equation could have a solution. You take a number and you add 1 to it and you get 0. That's impossible. Imagine that in the real world. How many, maybe, cows would you have, such that if you added one more cow, you had no cows? Well, it seems literally impossible to add something and then get nothing. How could you add 1 to something and get nothing? That makes no sense. But then, of course, we invented something very special. We invented negative numbers. And negative numbers, they might not be hard for you to grasp, but for many mathematicians across the centuries, the idea of a negative one, a number that was less than 0, a number that represented the lack of something, was completely foreign. But eventually, we as a species and as a set of mathematicians were able to agree that, okay, x equal to negative 1 is a number, it's a valid thing you can do. Well, the same thing happened with something like this. X squared plus 1 equals 0. How could you take a number and square it and then add 1 and get 0? It seemed like it made no sense. How could you possibly do that? Whenever you square a number, you always get a positive value. But then people said, well, do you always? What if you had something like this? What if you had a number x, we'll call it I, such that when you squared it, you got a negative number, maybe negative 1. Well, what that would mean is that x squared plus 1 would then equal negative 1 plus 1, which would be 0. And suddenly, hey, you'd have a solution. And the solution would be the number, well, I, where I squared is equal to negative 1. And for a long time, people freaked out because they said, how could you have a number that when you square it, you get a negative? But they said, well, it's simple. What that means is that that number is just the square root of negative 1. And you said, well, you can't square root negative numbers, but in the same way that you couldn't have negative numbers, eventually we decided you could, and in the same way you couldn't square root negative numbers, eventually we decided we could. And these numbers are called the complex numbers. So in the set of real numbers, negative numbers don't have square roots, but complex numbers were invented so that negative numbers would have square roots. And certain equations then have solutions. So these numbers are devised with the symbol I, which stands for imaginary. And I don't think imaginary is particularly useful because these numbers are just as real as any other number. But the other numbers are called the real numbers, so you needed a different name. So we call these real and imaginary. I think it's a bit of an unhelpful word for it, and so that's why I tend to call them the complex numbers. But to break it down, we have natural numbers, which are the whole positive numbers, then integers, which include the negatives, rational numbers, which include fractions, and then irrational numbers, and together this makes our friendly real number set. But of course, we can have imaginary numbers as well, and when we add those to the real numbers together, these two make up what are called the complex numbers. So let's look at a definition here. A complex number can be represented as a plus bi, where a and b are real numbers, and I, of course, is our imaginary number. So what we will say is, if we do RE, we mean the real part of a plus bi is just a. And if we say IM, we mean the imaginary part of a plus bi is b. So R means the real part, and IM means the imaginary part. So if our number was 2 plus 3i, well, we notice that there's a 2, a real number 2 there, and we notice there's a 3i, so the imaginary part would be 3. Now, this might seem very complex and weird and difficult to understand, but what we can do is actually visualize this. And so what we're going to do is make what's called the complex plane. And so on the x-axis, we're going to have the real part of the number, and on the y-axis, we're going to have the imaginary part. So what that means is the number 2 plus 3i means you go over on the x-axis, 1, 2, because it's two real parts. And then you go up on the y-axis, 1, 2, 3, because it's 3 imaginary parts. And 2 plus 3i is, well, right there, 2 plus 3i. And similarly, if you had negative 4 plus 2i, we'd go over negative 4 and up 2, or down, or right and down, etc., etc. So how does addition work with these numbers? Well, what we do is we treat I like a variable. So if we're going to add 4 plus 7x plus 1 plus x, what you would do is you would group those x's together and you would group the numbers together. And it's the same for complex numbers. So 4 plus 1 is 5. 7 plus 1 is 8. So 8i. Now, interestingly, we can actually visualize this on our diagram. So let's take the number 4 plus 7i. So that'll be 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. So right there, let's grab our point. And we can almost imagine this like a vector. So going over to 4 plus 7i. And then we're going to imagine adding on to that another little vector, 1 plus I. So we're going to go over 1. And we're going to go up 1, which will take us to right there. And if you look at our final point, it's at 5 and 8i. So there you go. Or another way to write it, right, is 5 plus 8i. So you could almost think of adding complex numbers similar to adding vectors. You put them tip to tail and you draw the first vector and then the second vector. Now, let's look at subtraction. So subtraction is the same as addition. You go ahead and subtract the real portion. So 4 minus 1 will give me 3. And then we subtract the imaginary portions. 7 minus 1 will give me 6. And to visualize it again, we can label our point here. So 4, 1, 2, 3, 4, 5, 6, 7. And again, this is kind of like a vector going up there. And then we turn the vector around when we do subtraction. We go back the other direction. So we go minus 1 and minus I. And that will end up, if you look at it, over at 3 plus 6i. So multiplication, well, again, you treat it like a variable, which means we will use our good friend FOIL. So we do first, 4 times 1 is 4. Outside, 7i times 1 is 7i. Inside, so 4 times negative I is negative 4i. And then last, negative 7i squared. Okay, well, we can group some of those together. The 7i and the 4i will clearly give 3i. But the other parts can't be grouped together yet. And we need to be careful. We have an I squared. There's nothing to combine the I squared with. But we can always remember that I squared is equal to negative 1. You can use that anytime you're working in complex numbers. So we're going to replace that I squared with a negative 1. And that'll give us 4 plus 3i. Negative times negative will be positive. And so our final answer will be 11 plus 3i. Now, division is a little bit more complicated. So for division, we can't really divide it like you would expect. There's no pieces to do, and so you say to yourself, well, how would I do division? And if you imagined this here, maybe like an x or like especially a root, you might say to yourself, well, I have 2 pieces, and maybe the conjugate will help. So just for fun, let's try doing the conjugate on this division question and see what we get. So we have 1 minus I, 4 plus 7i. Let's multiply by the conjugate. So 4 minus 7i, 4 minus 7i. All right, well, we have to do a lot of FOILs, so we're going to FOIL the top and FOIL the bottom. So 4 first, and then outside will be minus 7i. Inside 4i, and then last would be plus 7i squared. All right, on the bottom, we're going to get 16 minus 28i plus 28i minus 49i squared. Now remember, this is very classic. When you do the conjugate, the middle terms always cancel. All right, well, let's keep going here. So the top will simplify to 4 minus 11i minus 7. Well, I guess you could put plus 7 times negative 1 because we're converting that I squared. The bottom will be 16 minus 49 times negative 1. All right, we're getting close here. 4 and negative 7 is going to make negative 3. 16 plus 49 is going to give us 65. Now we only have one number on the bottom, so we're allowed to split that up as a fraction. So minus 3 over 65 minus 11 over 65i. And there we go. We know our number is finished. We've done the operation because we have it in terms of a number and another number with an I. A plus bi. This is the proper format for a complex number. You don't want to have anything left to do. There should only be two numbers and then the I next to it. Now the powers of I have an interesting pattern. If you look at I, of course it's, well, just I. But I squared is negative 1. Now what is I cubed? Well, using exponent rules, we know it's I squared times I. But I squared is going to be negative 1, which means it's actually negative I. Well, I to the 4, we could write that as I squared times I squared, which would be negative 1 times negative 1, which will be back to 1. So I to the 5 is, well, you could use I to the 4 times I. And I to the 4 we just showed was 1. So look at that. I to the 5 is back to I. So you have this interesting pattern where you go I, and then you go negative 1, and then you go negative I, and then you go 1, and then you go back to I. And so you go around and around and around and around in a circle, going from I to negative 1 to negative I to 1 back to I. See if you could determine I to the 23 or I to the 2019. Go ahead and pause the video and see if you can determine those values. So assuming you gave it a try, for I to the 23, what I'm going to do is count up by I to the 4s, because I to the 4 will be 1. So we have 4, 8, 12, 16, 20. So really, I to the 23 could be written as I to the 20 times I to the 3. And the I to the 20 part is just going to be a 1. And then I to the 3, we look up top, and it's negative I. So there we go. For 2019, we probably need to figure out how many 4s go in. So we're going to divide 2019 by 4. Bust out a little bit of long division here. 4 will go into 25 times. 0 times into the 1. 4 goes into 19 4 times. So we get remainder 3. So we could write I to the 2019 as, well, I to the, there's going to be a bunch of I to the 4s. In fact, there's going to be 504 of them. And then there's going to be an I to the 3 left over, which will give us 1 times negative I, which is just negative I. So you actually get the same thing. Now, the absolute value is used to measure the length of a real number. That's one way to think about absolute value. If you think about how big is the number 4, how long would it be on a number line? Well, it's 4. And the number negative 3, well, it's also 3. We don't consider that negative number because when you're talking about lengths, you always mean a positive. We can also use this absolute value, which we're now going to call modulus, to determine the length of a complex number. So let's see what this would mean. Well, if we draw this as a picture, we're 1, 2, 3 on the real axis, and 1, 2, 3, 4 on the imaginary axis. So this is our number 3 plus 4i. Well, how long is this number? What's the length of it? If you imagine this as a C, it looks like we could draw a little right triangle. 3 and 4. So 3 squared plus 4 squared would equal C squared. So that's going to give me 9 plus 16 equals C squared. So 25 equals C squared. So C is going to be equal to 5. And so therefore the length of the number 3 plus 4i is equal to 5. Okay, well, instead of drawing a picture in a triangle every time, we have this nice formula. If you're going to find the modulus, or the absolute value, or the length of a complex number a plus bi, you just do Pythagoras. You do the square of both of the values, and then you square root. So let's find the modulus of 10 plus 5i. So using the formula, this is the square root of 10 squared plus 5 squared. So 100 plus 25. So 125, which we could simplify as 5 root 5. Right, we can write that as 25 times 5, and then square root to 25. Okay, another thing we should learn about complex numbers. We have, again, the conjugate. So the conjugate of a complex number is just flipping the sign like we did with division, but we give it a special label. We call it z bar. We put a bar on top of the complex number, and that denotes doing the conjugate. So if our number is 5 plus 7i, z bar would be equal to 5 minus 7i. So let's do z equal to 3 plus 4i and find z bar. So z times z bar. Well, just so we have it here, z bar would be 3 minus 4i. So z bar is going to be 3 plus 4i times 3 minus 4i. All right, we'll do a little FOIL. 9, and then remember those middle terms are going to cancel, so minus 12i plus 12i minus 16i squared. Okay, so those middle terms, they're gone. And we have, well, 9 minus 16 times negative 1, so we have 25. If you remember from this number, we just did it up here, we found that the length of this number was 5. And apparently when you do z bar, you get the number 25. Well, it just so happens that that's not a coincidence. We have another excellent formula. If you want to find the square of the length, or the square of the modulus, you just do z bar. Alternatively, if you find z bar, you're going to get 25, which means you could square root that final answer and get your length. So if z is equal to 3 plus 4i, we could find the modulus like this. Z bar is equal to 25 from above. So therefore, the modulus of z is going to be equal to the square root of z bar, which is the square root of 25, which is 5. Now, you might like the first formula better, and that's fine. There's no preference here, but it's just a neat example that whenever you multiply a complex number by its conjugate, you get the square of its magnitude, or the square of its length. Now, a few more things to note about complex numbers. If z is equal to 3 plus 4i and w is equal to 5 minus 2i, let's determine the conjugate of z plus w, or let's find the conjugate of z and the conjugate of w and add them. Well, okay, let's do this first one. And to do that, we should find z plus w first. So z plus w, so that's 3 plus 4i plus 5 minus 2i. So that would be 8 plus 2i. Okay, so then the conjugate of z plus w will be 8 minus 2i, because we just flipped that sign. Well, let's find the z bar instead. That'll be 3 minus 4i. Well, let's find w bar. That'll be 5 plus 2i. Well, let's add them. So 3 minus 4i plus 5 plus 2i gives me 8 minus 2i. Hey, wait a minute. Aren't these two the same? Well, indeed they are. And this is an interesting property about complex numbers. It's a theorem. You can either do the addition and then do the conjugate, or do the conjugate and then do the addition. Either way, you're going to get the same number. And so this is a nice little chance for us to do a theorem, and we're going to show how to actually prove this. We need to do it in general. So we're going to let z equal to a plus bi, just a general complex number. And w is going to be, well, we need more letters, so c plus di. So we'll start with the left-hand side, so z plus w bar would be, we're going to leave the bar over top of it, so a plus bi plus c plus di. Well, we add the real part, so it's a plus c, and then we add the imaginary part, b plus d, and put an I there. And it's still got a bar because we haven't done the conjugate. Well, notice we now have it as a number plus a number times I. So it's in its proper form, and we can do the conjugate, which means this number here is going to become negative. We switch the sign. All right, well, we can drop the brackets now. It's not as necessary. And we're going to distribute that, so negative bi, negative di. What we're doing here is we are distributing the negative in, and we're also distributing the I. All right. Well, we could go ahead and rearrange this. We could put this as a minus bi plus c minus di, which just so happens to be z bar and w bar. And there's our proof. So for homework, please try these questions on complex numbers. They're just to get a hang of how complex numbers work. There's some basic addition and multiplication. There's a little bit of algebra where you solve for x. And there's a few proofs to take a look at. As well, of course, as some examples of finding the length. So make sure you do these and get comfortable with complex numbers. If you need to, you could always make up a few of your own examples. And then in the next video, we're going to look at using complex numbers to solve some complex equations. So until next time, thanks for watching.